Hello, ladies and gentlemen. Today we are going to look at surface area and volume of spheres. So spheres are like the balls that you have tennis balls and baseballs and all kinds of round, circular, three-dimensional objects. Spheres, though, are defined a little bit differently. It's the set of all points in a 3D space that are the same distance from the center. So if you just keep going out like from a center with a string to all these different areas, that's how you create a sphere. So the set of all points in a 3D space that are the same distance from the center. It's kind of an interesting way to define it that maybe you have never thought about. You have an idea of what a sphere is, but maybe not what the formal definition is. So how do we find the surface area of a sphere? Well, one way to look at it is you can see this sort of baseball right here, and if you take the covering off, what you really kind of have is the surface area. And it's sewn together, but you can see that there are some overlapping pieces right here where they're stitched on top of each other and so forth. So this is actually right from the textbook. You can go back and read it, or you can read it yourself right here about how that relates to the surface area of a sphere. What's even more cool, and maybe an easier way for you to remember it, is to cut and paste this into a browser, and it shows you a video of how you look at the surface area of, let's say, like an orange. Because if you peel off the peelings of an orange, what you really have is the surface area of that orange, of that sphere. And in this video, a person takes the peelings off and puts them into circles, okay, the same size that they would trace here, that would be the largest diameter going around. And it turns out, and like I said, it's really kind of an interesting video, kind of cool, is it turns out that the surface area of a sphere ends up to be made up of 4 two-dimensional circles. So in other words, the orange peels filled up 4 circles, okay, that were this area, okay, the largest, basically the area of that flat 2D surface. So the surface area of a sphere is simply 4 circles, or 4 pi r squared. Pi r squared is 1 circle, multiply it by 4. Pretty simple. Okay, pretty straightforward. So let's look at the volume. Volume's a little bit more complicated. And again, this is taken right from your textbook, okay? And you can kind of read through it. Some of you, I would challenge you to try to understand how the formula simplifies all the way down here to 4/3 pi r cubed, okay? And it's kind of based on the fact that you could take a sphere and you could make up a bunch of pyramids where the point or the vertex is the center of the circle, and you're going out and you have all of these flat little surfaces, and all of those pyramids combined, here's a bigger drawing of it, make up the surface area. Well, this video down here, also, I would cut and paste into a browser because this video is pretty deep, but it's pretty cool. And some of you need a little bit something to challenge yourself in these days when we're not face to face. But I would encourage you to go and watch that video and see if you can understand where this is all coming from, because it really turns this whole pyramid idea into this simple formula for a volume of a sphere. So the volume of a sphere is 4/3 pi r cubed, where r is the radius. So actually, probably the good news is surface area and volume of spheres are pretty easy. They're a lot easier than the pyramids and prisms that we've had to do with calculating apophthegms of regular polygons, and even sometimes trying to find slant height and so forth. So what we're going to do here is we're going to calculate the volume and surface area of a couple spheres. So it says, below are the radii of various sports balls. Find the exact and approximate surface area and volume, okay? Well, since it's spring right now, let's take a look at a baseball, and let's compare it to a lacrosse ball. So if we talk about the surface area, remember it's 4 circles, so it's 4 pi r squared. So for the baseball, our radius is 3.56. So we have 4 pi times 3.56 squared, which is approximately 159.26 centimeters squared. Remember, surface area is square units because it's around the outside surface. Well, let's take a look at the lacrosse ball. Okay, so again, surface area is 4 pi r squared, 4 circles. And we can see the radius of our cross ball is 3.13. So 4 pi times 3.13 squared. And that is approximately equal to 39.19 centimeters squared. So even though the radius of both of those, the baseball and lacrosse ball, are 3 point something inches, the surface area is definitely a lot different. And so start to take notice of how that changes. And compared to the radii, and it kind of goes back to what we learned in chapter 11, where if we knew the side length of two similar solids, or that's what we're going to do tomorrow, if we knew the side length of two similar polygons, we knew the areas were not the side lengths, but the side length squared ratio. Well, that's the same with spheres. When we look at spheres, they're all similar to each other. And so what happens is that the areas are not just the same ratio as the side lengths, but they're going to be the side ratio squared. So just kind of notice that as you're calculating some of these things. So let's take a look at volume. So the volume of the baseball would be 4/3 pi r cubed. So we have 4/3 pi times our 3.56 cubed, which calculated would be about approximately 188.99 centimeters cubed. Lacrosse ball, volume 4/3 pi r cubed would give us 4/3 pi times 3.13 cubed, which is approximately equal to 123.11 centimeters cubed. Oh no, I'm sorry. That actually, I think I have these values incorrect here. I was trying to save myself some work and I recopied some things wrong. So let's go back here and here because I recorded information incorrectly, as you probably figured out when calculating on your calculator. So this is approximately 128.45 centimeters cubed. And if we go back to the surface area of the lacrosse ball, it is actually approximately 100. Oh, I see. I calculated it in exact. These are both. There we go. So the other values were the exact. So I did both all of the approximate. If you want the exact, you just do it in terms of pi. So pay attention to that little tidbit too, that if they're asking for the exact versus approximate, remember exact is in terms of pi. I think this will be pretty straightforward and easy for you guys, but I am going to be available to answer questions. Let's just take a look at one more where we work backwards. I'll work this one out for you in the notes, so you can check out the notes for this one. But let's take a look at this next one where we at least work one backwards. It says a decorative ball filled with water has a surface area of 1600 pi square units. So 1600 pi square units, that's what we're talking about when we mean exact. We didn't multiply that by pi. So we know our formula for surface area is 4 pi r squared because it's 4 circles. So now we put our surface area in, and we are trying to find how much water the ball holds, which is going to be the volume. So in order to find that, I'm going to have to use the surface area with 4 pi r squared and solve it to find my radius. So I can divide each side by 4 pi, which those cancel out, 4 pi, and what that gives me is 400 is equal to r squared, so r is 20. So now I can go ahead and take my r in my volume formula. Volume is 4/3 pi r cubed, so how much water holds will be 4/3 pi times 20 cubed, which is approximately 33,510.32 square units, so units cubed actually, units cubed. Okay, so volume surface area of spheres, okay, pretty simple. There's also, this one's a little interesting to think about. When you're talking about a tennis ball container contains 3 tennis balls that are stacked vertically and exactly touch the bottom and top of the can. It gives you the diameter of one tennis ball is 6.7 centimeters. How much space is wasted inside the can? So what you have is you have a cylindrical can like this, and you have 3 tennis balls stacked inside, okay? And they're stacked vertically and they exactly touch the top and the bottom. So then what you do is you take that information and it tells you the diameter of one tennis ball right here. So this one tennis ball diameter is 6.7. And so that means the diameter going this way, because it's a sphere, is also 6.7. So see what you can think about the setup for this one, for finding how much space is wasted, because you're going to have to find the volume of the tennis balls, so volume of one tennis ball times 3. Then you're going to have to find the volume of the cylindrical can and subtract the tennis balls from it, and that will be how much is wasted inside the can. Okay, so again, check the notes and I'll work that one out. All right, here's your learning targets and homework. You choose, but I have a starting point for you, but make sure you're practicing enough and you're checking your answers. Have a great day, everyone.